Welcome to this Optimize This video, a series of videos focused on applications of HEADS in industrial applications. Our focus for today is on leveraging HEADS to help your organization attain robust CAD, critical for any design space exploration. However, it should be noted that even if not using design space exploration as part of your simulation workflow, HEADS can help your designers develop more robust CAD within their existing design process as well. Today's presentation was developed by Dominic Barsotti, a member of the Global HEADS technical team. We'll begin with a look at today's agenda. We'll first introduce the importance of robust CAD. We'll then look at what CAD robustness is and entails. Finally, we'll take a look at how HEADS can help enhance your processes to make robust CAD a part of your standard design process. Let's get started. Why is CAD robustness important? As this is a HEADS Optimize This video, we are proceeding with the assumption you are already familiar with HEADS and its optimization approach. Imagine you are HEADS Optimization Search Framework (SHERPA) trying to make sense of an unknown problem. You are presented with only a small portion of the results from which you are making future decisions. This is equivalent to us trying to determine what this sentence means. In it, 50% of the answer is missing. It can be very difficult to determine the correct answer with only 50% of the needed information. The same is true for SHERPA. Having only 50% of the information from the design space makes it very difficult to find innovative solutions. This is where CAD robustness comes into play. Error designs are the equivalent to the missing information from this sentence. With a reduction in error designs, meaning the CAD is more robust, we are reducing the amount of missing information. If we are presented with more information, the sentence becomes much more clear. Now we can see 70% of the same sentence and the answer becomes discernible. The same is true for SHERPA. Presented with 70% of the design space, it has a significantly higher chance of finding high-performing solutions. The answer becomes clear with enough data to navigate and sort through to the solution. As Shakespeare said, "To be or not to be, that is the question." Here the question is whether your design team is giving enough information to SHERPA to make informed decisions. More generally, is your CAD robust enough to provide a clear path to the innovation solution your organization is seeking? As it pertains to optimizing with HEADS, we need to give sufficient information to SHERPA to seek the design landscape. This starts with robust CAD. HEADS can help us to get to a state of robust CAD through a CAD robustness study upfront, prior to incorporation of the simulation models to assess performance. CAD robustness is an assessment of a CAD model's ability to regenerate successfully when changes are made to the model. In the context of HEADS, this robustness is assessed against parametric variation of variables against the intended variable range spectrum, encapsulating the intended variation in designing the product. A study can be performed in HEADS to assess this robustness with what we term a CAD robustness study. Here, after a parametric CAD model is built, that model is added into a HEADS project with variables covering the intended range for a design space exploration. The CAD is then exercised across the variable range to understand not only the rate of successful generation, but also to help identify regions in the design space that are error-prone, or relationships that persist amongst the CAD parameters. The goal of a CAD robustness study is to have greater than 70% successful regeneration through HEADS. The reason goes back to the Shakespearean example we saw earlier. Usually, if less than 70% success rate, the design landscape is hard for the optimization search framework to search over efficiently during a design space exploration. A CAD robustness study can be created either just with the CAD incorporated or after an entire workflow is developed in HEADS. If after a workflow is developed, the simulation tools can be disabled such that only the CAD tool is enabled for the robustness assessment. Doing so enables rapid assessment of the CAD and, if necessary, the ability to refine and iterate quickly to get to a state of suitable CAD robustness without extensive simulations adding time. For CAD robustness studies, a Latin Hypercube or optimal Latin Hypercube sampling should be utilized to search the design landscape evenly. With an understanding of what CAD robustness is and why it is important, let's now look at a case study that showcases how HEEDS can enhance your CAD robustness endeavors. To do this, we'll look at an application example where we are tasked with designing a static air mixer. Here, a device is placed in a pipe to mix stratified air where at the inlet of the pipe we have hot air entering at the top and cold air entering at the bottom. Just beyond the inlet we place the device which is to be designed. The goal of the device is to mix the stratified air to achieve homogeneous output downstream. This is a computational fluid dynamics problem where using SimCenter star CCM+, the virtual performance can be assessed for a given device. Ultimately, our optimization goals with HEEDS are to minimize the temperature variation at a cross-section downstream of the device while maintaining a pressure drop constraint threshold. Our workflow will ultimately be CAD providing updated geometry for the device into a downstream SimCenter star CCM+ analysis. However, for our purposes, we're going to focus solely on the CAD portion of our workflow. Before investing in the computationally expensive CFD simulations, we first need to ensure our CAD is robust. If we look at our static air mixer device, we can see we've developed a device made up of inner and outer concentric circles with blades connecting the two. The concentric circle details, along with the number and shape of the blades, are to be designed to achieve our temperature uniformity goals. A parametric model has been developed with 5 variables. The occupy ratio gives the relative ratio between the size of the inner radius to outer radius of the 2 concentric circles. Additionally, the number of blades are designable. For each blade, a pitch angle is defined, with the same angle common across each blade. A parameter called curvature strength is used to define the amount of curvature on the blades. An additional parameter, curvature position, defines where that curvature occurs along the blade. Our design department has developed a parametric model in CAD to capture these intended variables against our prescribed intended variable variation, shown here in the table. Upon receipt of the parametric model from the design department, we set out to assess the CAD robustness. As I'm sure is common within your organization as well, our designers were quite confident in their parametric build, having done a customary spot check and variable extreme design of experiments upfront before delivering the model to us. Leveraging the direct portal in HEEDS to CAD, we were able to rapidly set up the automated study in HEEDS. Having defined the intended variable ranges and ensuring SimCenter star CCM+ was deactivated, we launched a Latin Hypercube sampling study for CAD robustness assessment. Upon doing so, we discovered that the CAD parameterization was not as robust as anticipated or desired, with a 39% success rate or 61% error rate. While HEEDS has identified for us a high error rate with our CAD, that by itself is only the beginning of the value HEEDS has to offer in helping us make our CAD robust. We can leverage HEEDS Post to help us understand why the high error rates persist and to guide us toward how to fix the issue or issues. Here we see a 2D relation plot in HEEDS Post where a parameter CAD success indicates to us whether a design was successful or not. A value of 1 indicates success, while a value of 0 indicates an error, meaning the CAD couldn't successfully regenerate. Along the x-axis we have plotted the variable values for curve position, one of our 5 variables. Each point represents a design evaluated as part of the CAD robustness study. Here, there is no evident trend identifiable since the variable combination seems semi-evenly spread amongst successful and error designs. However, if we look at the other 4 variables as well, some trends jump out at us. Notably, the sparse concentration of successful data for low values of the variable rotate angle and high values of curve strength are revealing. From this, we can see that when values for rotate angle are less than 10, the majority of the error designs occur and very few successful designs were evaluated. Similarly, when values for curve strength are greater than 0.9, most designs are error designs. So what can we do now? Of course, the simplest solution is to simply change our variable ranges in HEADS to eliminate the two problem areas. However, there are problems in doing so. First, we've now altered our intended variable ranges from what was decided upon initially, presumably selected based on solid rationale. If we alter the ranges, we risk stifling our innovation potential, as we are now reducing the potential concepts from those originally intended. Additionally, simply changing the variable ranges won't solve the underlying issue in the CAD preventing the regeneration, but rather put a band-aid on a problem. It is probable that by taking a deeper look at the CAD, other problems may be identified in how the parametric model was built. A better approach, therefore, is to go back to the CAD to understand why these errors are occurring. HEADS Post has identified a problem in our parameterization, which is valuable insight for our designers to interrogate. In our case, when we look at the CAD, our designers are easily able to identify a problem. When values of rotate angle become too small, a slice feature built into the CAD fails because the parent sheet feature used to perform the slice operation fails because the blades don't extend far enough. This is easily fixed by our designer by extending this surface in both directions in the base CAD. Rerunning the CAD robustness with this simple fix increases the robustness of the CAD, reducing the error percentage from 61% to 46%. When our CAD team does the same assessment to try to understand why the CAD is failing when curve strength is above 0.9, however, no discernible trend is identified. We need to post-process in HEADS Post more to understand what is going on with this issue. A parallel plot is one of the most useful data mining plots available in HEADS Post. It allows for visualization of the entire design landscape. Along the x-axis of the plot are the parameters. Here are measure for successful or error CAD, along with our 5 variables. Along the y-axis is the parameter range for each parameter. If we look at occupy ratio, for instance, the design space spanned from 0.2 to 0.8 over the course of the design space exploration. Each line on the plot represents a design from the exploration. The intersection of the line with the parameters gives an indication of the design's location within the design space. Here, 2 design sets have been plotted on the parallel plot. The blue designs represent the successful designs, where the CAD successfully regenerated, while the red designs represent the error designs, where regeneration wasn't possible. This plot therefore can help us quickly uncover trends. We can easily see, for instance, the limitation on curve strength identified earlier, where values above 0.9 typically cannot regenerate. However, we can use the fact that we are viewing all parametric values simultaneously to our advantage to also see what relationships may exist amongst the parametric combinations. Rearranging parameters such that we explore their placement beside each other on the plot can help make these trends obvious. Plot settings allow for easy control of the order of the parameters on the plot. Here, we'll move the troublesome parameter across the variable spectrum in terms of positioning to see if any discernible relationship is evident. If we move curve strength next to occupy ratio, a trend begins to become visible. As seen by the slope direction between occupy ratio and curve strength, lower values of occupy ratio in combination with higher values for curve strength result in error designs. Stated differently, positive slopes as shown between the 2 parameters result in errors, while flat or negative slopes result in successful designs. With this new knowledge in hand, we can return to the CAD model to understand why this relationship exists. When a positive slope occurs, meaning the occupy ratio is less than the curve strength parameter, the blade loses contact with the inner circle, causing CAD failure. Variable relationships within HEADS can then easily be deployed to enforce the relationship that the occupy ratio must be greater than the curve strength. This relationship can be enforced with a relationship feature in HEADS or with a semi-independent variable approach. Please refer to other knowledge articles devoted to each of these topics for more information. Utilization here now gets the error percentage reduced to 20% within the target for CAD robustness. Recall, we are striving for 30% or less error designs from a CAD robustness study in HEADS. equating to a success rate greater than 70%. We've achieved our goal. The techniques used here solved our issues for this particular problem. What is right for your problem could be entirely different. What is important to know is that HEADS has the toolsets available to diagnose and help fix the problem, achieving your required CAD robustness for your problem. There are various options available to make your CAD more robust. You could do nothing, resulting in a discontinuous, difficult design landscape to search from an optimization perspective, additionally, limiting your potential for rapid CAD changes manually. You can take the easy approach of altering variable ranges in HEADS. This approach is within the HEADS user's control and is easy to implement. However, it is altering the originally intended design landscape, potentially reducing innovation potential. Either variable relationships or semi-independent variables can be utilized in HEADS to enforce relationships amongst variables to enhance robustness. Each of these approaches have their pros and cons as listed here. Or CAD modeling approach alteration can be used to enhance robustness while allowing for the original variable definitions to remain. Typically, this approach requires strong collaboration between the designer and the HEADS user and can be slower to implement. In this video, we've shown how a combination of modifying the CAD in combination with a relationship definition in HEADS can take very unreliable CAD alterations and make it very robust. To summarize, CAD robustness is an important aspect of design and critical to parametric optimization, as can be done with HEADS. A CAD robustness study should be performed anytime CAD alterations are to be incorporated in a design space exploration, and should be done independent and upfront of simulation automation within HEADS. Various solutions are available within HEADS. In this presentation, we focused on diagnosing as opposed to implementing solutions to improve CAD robustness. Individual separate topics are available as various knowledge articles to detail the solution implementation. Optimal Latin Hypercube studies for CAD robustness can not only help diagnose, but also offer solutions to making CAD robust against the intended variation for the product design. It should be a critical toolset in helping build robust parametric CAD models and is available for simulation engineers and CAD designers alike to benefit from. Thank you for watching this Optimize This presentation. The content of this presentation was developed by Dominic Barsati, Senior Application Support Engineer on the HEADS Design Exploration Team. As always, we encourage you to benefit from the various resources available for learning more about HEADS in terms of applicability and utilization. Thank you for watching.